All right, everybody, get ready for a wild one today,
Mm-hmm.
because we are diving headfirst into a physics mystery that just might turn everything you thought you knew on its head. We're doing a deep dive into something you probably heard of, probably even learned about back in school, the photoelectric effect. Shine a light on something, electrons go flying, and bam, instant proof that light was really made up of particles, those little bundles of energy we call photons.
Huh. What if I told you there might be another way to think about it? What if you could ditch the whole photon idea altogether and explain this whole thing using classical physics?
Now that's a head scratcher, isn't it? It sure is. And that's exactly what we're exploring today with this paper, Photoelectric-Effect.pdf by Sergey A. Rashkovskiy. This researcher is on a mission, and that mission is finding classical explanations for things we usually think absolutely require quantum mechanics to explain. Talk about shaking things up.
He's definitely not afraid to challenge the status quo, that's for sure. And the way he goes about it is fascinating.
So spill the beans with his big idea. I've heard whispers. Something about electrons,
Yeah.
not as particles.
You heard right. Get this. He's proposing that we think of electrons not as those little tiny particles we always picture, but as, get this, continuous charged waves. That's right, waves.
Waves. Electrons as waves. Okay, I'm picking up what you're laying down. It's a bold claim, but I've got to say, it's intriguing. But how does it actually work? How do you explain something like the photoelectric effect, with all its established laws and experiments, using waves instead of particles?
That's the really cool part. What's so fascinating about this paper is that it doesn't just throw out this wild idea and leave it at that. It backs it up, and I mean really backs it up, with math. Rashkovskiy uses classical field theory to actually explain mathematically those cornerstone laws of the photoelectric effect that everyone learned in physics class.
Okay, so no hand waving here. He's got the equations to back it up. I like it. So let's dive into those laws then, shall we? First up, the stronger the light you shine, the more electrons you get. That one makes sense intuitively, even if you've never taken a physics class in your life. More light, bigger effect. But what's the wave explanation for this?
Picture this. The electron is a wave, just vibing out, doing its thing. Now, a light wave comes along, and remember, light is also an electromagnetic wave and smacks right into that electron wave. The stronger the light wave, the bigger the push it gives the electron wave. It's all about energy transfer, pure and simple. And what Rashkovskiy does is he actually shows mathematically, using good old-fashioned classical physics, how that energy transfer from the light wave to the electron wave leads to a stronger electrical current. It's elegant, really.
Okay, I'm not gonna lie. That is pretty darn cool. So we've got law number one covered. Now, on to the third law. The frequency limit. Shine a light below a certain frequency and you won't get any electrons, no matter how bright that light is. It's like trying to push a swing. If you don't time your pushes just right, it's not going to get going no matter how hard you push.
You've got it. That analogy is spot on. And this, my friend, is where this whole wave model really starts to shine. You see, if the electron is a wave, it has a specific frequency at which it vibrates. And the light wave, well, it has a frequency too. And those two frequencies, they have to match up.
They have to resonate, right?
Exactly. They need to resonate for that light wave to transfer enough of its energy to actually kick the electron out of the atom. Below a certain frequency, that light wave just can't get the electron wave going enough for it to escape the pull of the atom, no matter how intense it is.
So it's not just about brute force. It's about hitting that sweet spot, that resonant frequency, which, if you really stop and think about it, starts to make the whole idea of electrons being these teeny tiny billiard ball particles seem, well, a little strange, don't you think?
It really does make you wonder, doesn't it?
It sure does. Now, on to the big kahuna, the law that seems to really point to photons, those little packets of light energy being the only possible answer, the second law. This is the one that says that the energy of those emitted electrons, those ones that actually make it out of the atom, depends only on the light's frequency, not on how bright it is. It's like each electron knows exactly how much energy it's supposed to have based solely on the color of the light, not on how strong the light is. That's why we came up with the idea of photons in the first place, isn't it? To explain those discrete energy levels.
Right, you're exactly right. And this is where things get really, really interesting. Because if Rashkovskiy is right and electrons are actually waves, well, this whole second law takes on a completely different meaning. See, he's suggesting that we're not actually measuring the energy of individual electron particles at all. Instead, what we're measuring is the energy that's distributed within that emitted electron wave.
Okay, I'm following you so far. So the energy of the wave itself, not individual particles.
Yeah.
But how is that energy determined?
That's the key. That energy is directly related to the frequency of that emitted electron wave.
Hold on. Let me see if I got this straight. You're saying the frequency of the light wave determines the frequency of the emitted electron wave, and that's what we're actually measuring when we talk about the energy of the electrons.
Bingo. You got it. It's like, how should I put this? Imagine you're tuning a radio, right? You're fiddling with the dial, trying to find that sweet spot where the signal comes in crystal clear. You're not blasting the signal with more power. You're adjusting the frequency to find that perfect resonance.
Okay, yeah, I did.
And that's what determines the energy of that emitted electron wave, which we then measure and interpret as the energy of the electrons themselves.
Wow, okay. So just to recap for a sec, we've covered the three main laws of the photoelectric effect, the ones they drill into you in every physics textbook. And Rashkovskiy is saying we can explain them all without ever even mentioning the word photon, just by thinking of electrons as waves, not particles. That's a pretty big deal in and of itself, but I feel like we're just scratching the surface here. What are the bigger implications of all this? Where does it lead us?
Well, let's take a step back for a second. Think about what this means in the grand scheme of things. For over a century now, the photoelectric effect has been held up as this, ironclad piece of evidence for the quantum nature of light, right? Yeah. It's literally in every single introductory physics textbook. But if Rashkovskiy is onto something here, if his theory holds water, it could mean that we've fundamentally misunderstood what's going on at that level all along.
That maybe it's not about particles at all, but about waves.
Yeah.
Waves interacting with waves.
Exactly.
Okay, yeah, I see where you're going, Wes. This is big, even paradigm shifting, maybe. But what about all the other experiments out there? The ones that seem to back up the idea of photons? I mean, there's a whole mountain of evidence for quantum mechanics, right? How does this wave-based view fit into all of that?
You're right to ask that. And the really cool thing is that Rashkovskiy actually addresses some of those other experiments in his paper. One that he talks about that I found super interesting is the Meyer and Gerlach experiment. Ever heard of it?
Meyer and Gerlach. Yeah, it's ringing a bell. Did they shine UV light on tiny metal particles or something?
That's the one. And what they found was that those metal particles would emit electrons almost instantly as soon as the light hit them.
Yeah, okay, now I remember. The idea was that the electrons were each getting hit with these concentrated little packets of energy photons, and that's what allowed them to be ejected from the metal so quickly.
Exactly. The assumption was that if light were truly a wave, then the electron, as a particle, would need time to absorb enough energy from that wave to break free. It'd be a slower process, right? It'd have to, soak up enough energy before it could escape.
Right. Okay, I'm with you.
But here's the kicker. If the electron itself is a wave,
then it can start interacting with the light wave instantaneously, no matter how strong or weak that light wave is.
You got it. It becomes a continuous process. There's no waiting around for enough energy to build up, no need for this idea of the electron needing to be hit with enough force to be knocked loose. If it's a wave, it can just kind of ride the wave out of the atom.
Yeah, like catching a wave on a surfboard.
Precisely. And that's not all. This whole wave-based view also throws a wrench into other quantum phenomena as well, like the ideas of multiphoton ionization and tunnel ionization.
Refresh my memory. Those are.
So multiphoton ionization is where an electron supposedly needs to absorb multiple photons at once to gain enough energy to break free, and tunnel ionization is where it supposedly tunnels through an energy barrier to escape.
Ah, right, of course. Quantum weirdness at its finest.
Exactly. But what Rashkovskiy's model suggests is that maybe, just maybe, these processes don't involve photons at all. Maybe it's not about these individual energy packets, it's all about the dynamics of waves interacting with each other.
So even a weak light wave can still have a major impact on an electron wave, as long as their frequencies are in sync.
Now you're getting it. It could be that we've been so focused on this particle picture, this idea that everything at the smallest level has to be these tiny little points of matter, that we've completely missed a much simpler, much more elegant explanation staring us right in the face.
Wow. I have to say, you've given me a lot to think about today. This is really making me rethink everything I thought I knew about quantum mechanics. It's like we've been looking at this whole thing, this photoelectric effect, that's so fundamental to how we understand light and matter, through the wrong lens this whole time.
And that's the beauty of science, isn't it? Always questioning, always digging deeper, always open to new ways of seeing the universe.
It's amazing to think about, It's like the universe is this endlessly fascinating mystery, and we humans, we get so used to our explanations, our models, our theories, that we sometimes forget to keep searching for those deeper truths. And you know what I find really cool about all of this? It's not just about poking holes in the standard model.
Yeah.
It's not just about saying, hey, everything you thought you knew about photons is wrong. Rashkovskiy is actually offering a whole new way of looking at these phenomena, a whole new framework for understanding how light and matter interact. And the best part is, it feels surprisingly intuitive.
It really does make you wonder if we've been making things more complicated than they need to be. What other quantum mysteries might we be able to explain in a more elegant way if we just shifted our perspective a little?
It's like we're on the verge of a whole new era in physics, moving away from this idea that everything is a particle, and rediscovering the power and the elegance of waves. Think about it. It's waves all the way down.
Exactly. And the thing is, this isn't just some fringe theory, some wild speculation with no basis in reality. Rashkovskiy is using established physics, the same equations that have been around for over 100 years, to back up his claims. He's just approaching them from a different angle, looking at them with fresh eyes.
Which is what science is all about, right? Challenging assumptions, looking for new perspectives, pushing the boundaries of what we think we know.
Absolutely. That's how we make progress.
It just goes to show that sometimes the biggest breakthroughs don't come from inventing brand new physics, but from taking a fresh look at the old physics and seeing it in a new light. Pun very much intended.
You got that right. A little physics humor to brighten your day.
So if there's one thing you take away from this deep dive today, let it be this. Don't be afraid to question what you think you know, even, or maybe especially, in a field like physics that we tend to think of as being so cut and dry. Who knows, you might just stumble upon the next big revolution in our understanding of the universe.
Now, wouldn't that be something?
It sure would. And if you're as intrigued by all of this as we are, and I have a feeling you are, we've got a link to Rashkovskiy's full paper in the show notes for you. It is, without a doubt, a wild ride, and we highly recommend checking it out.
It's a real mind bender in the best way possible.
It really is. Well, on that note, I think we've done enough deep diving for one day. Until next time, keep those minds curious, keep exploring, and we'll catch you on the flip side.